I feel there should be a song here. But now we are looking at, and I need to stop waving my hands because it's very distracting to me. We are looking at Faraday's second law. So first law was about that time and that ratio of going up. Now we're getting a bit more complicated and we're looking at what electrons are doing and how that can then be used to work out time and mass. And again, it's that industry thing. So I'm making things, doing things, covering my scooter with chromium or whatever it is, and I need to work out how long it's going to take to get the amount I need. Think about in industry, they want to have the bare minimum that they can get away with. So I've got a scooter or a piece of jewellery or a spoon or whatever. I don't want to put loads and loads of silver or chromium or whatever it is on it. I want to do the bare minimum I can get away with and have a decent product. So I want to do it as cheaply as possible, and that means having as little product applied to whatever it is that I want. So I've got this ratio between, I should get my thing right. God, I'm really annoying. A ratio between the number of electrons we have that we put into our system to turn our ions into a solid, and the amount of solid that we get. So there's this relationship, and that's part of our Faraday's second law. I'm going to turn this around because that's a bit better. It's a bit wonky. Oh, it'll do. Right. So this is Faraday's second law. So we've got this ratio of moles. So if we have So I'm always going to need these 2 electrons in my solution to be balancing out to make my solid. So there's always going to be this ratio. And then there's going to be, like, just if I have Fe3 plus, I'm going to need that 3 electrons to make the solid. Oh my god. Right. So, you can see that you've got this relationship between the number of electrons I need to put into my system to go from my nice solution to go to my solid. So if I'm doing my spoon, or if I'm covering something in chromium, or I'm analyze it. If I'm covering a tin can with some aluminium or something, I need to know how many electrons that I've got. So there's this ratio, and I need, for this one, I'm going to need 1 mole of electrons to produce 1 mole of my silver, gold, silver. I never remember. Right, 1 mole of my metal. With the iron 2, I'm going to need 2 moles. Iron 3, I'm going to need 3 moles. So there's going to be this relationship, and that's kind of the underpinning of Faraday's law. Be very careful when you're reading it, because some of them I was looking like, what are you waffling on about? Where are you going? And they say you need whole numbers of moles. So I read some things about you need whole numbers of moles, and that, I think that makes it more confusing than it needs to be, because if I've got half a mole of this, well, I only need, if I've got 0.25 moles of this, let's say, well, I'm not going to get the same. It's not going to be, it's just this ratio thing rather than you think 1 mole, 1 mole. Because if you start thinking you have to have whole moles, well, you don't need whole moles, because you're not going to have whole moles going in. So, there's a lot of information in here, but a lot of it you get given in the data book. And it's about you using that data book and getting used to what it means, and that link between what you see on that page and how you think of using it. So taking that link that we had of someone who's already done the annotations and thinking about what that data book means and why they've given you the things they've given you. So each little one of these electrons has a charge, and that's a known charge. Some French guy that I can't remember the name of worked it out and measured it, and we're just assuming that that's what it is. They give it to you in the data book, and it is that's a minus 61 times So each and every one of our electrons has a charge of minus 1.6 times 10 to the minus 19 coulombs. Still not convinced I'm saying that right. So that's what each and every electron has. So if I've got 1 mole of electrons, so with this one, I've got 1 mole, I want to make 1 mole of this. So how many electrons am I going to have to put in to my solution? And I do that by electricity. So this is my electricity being putting in these electrons, and this is in solution, or is being taken off a silver rod, like we talked about before. I say we, as if it's... I can work out how many my mole. Right, so charge of a mole of electrons. So if I have a mole of electrons, what's the charge of that going to be? I'm going to go that way because I think I'm writing too far away. The charge of a mole of electrons is the charge of 1 electron times how many electrons I have in a mole, which is my Avogadro's number. Because I learned my lesson last time, I worked this out beforehand, and I didn't need to work it out because it's in the data book. She says checking. And this is my Faraday. So I talked about this Faraday's before. We didn't come onto it, but I was, that kind of vocab list I was giving you. But this is Faraday's number. There's a charge. It's got a C. Sure that's. So this is for a mole of electrons. That's my charge. I've got a mole of them. That's going to be my charge. If I've got any number of electrons, so this is why I think the one-to-one thing gets confusing. I can use this, I can use the information I've given, and I can work it out. And this is all numbers in your data book, so this is not stuff you have to remember how to use it, but not what it is. So, right, so this is our number of moles of electrons. This is my Faraday's constant. So I'll take a picture of my working out for it because I think this is the kind of stuff you generally do okay in because it's just that maths. So I'll put the question up. If you have more questions about it, just have a look at the questions because I think you can go backwards and forwards when it's these maths questions and you can see step by step. And hopefully my vague explaining in the book is easier than me trying to do it like this. But there's this, if I've got this many electrons, which is 10, then I've got 10 times this. If I've got 100 times. If I've got half, it's going to be half. It's just that, simple maths. So that's our first law. So there's just this relationship between our electrons and our first law, second law. No, not second law. So there's this relationship. But what we can do is we can take the first law and we can take the second law and we can use it to actually figure out important stuff that we need for producing things or manufacturing or working out time. So, time is money. You want to do things as quickly as possible, cheaply as possible, blah, 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 all that stuff. So we've got this one that we can rearrange as our triangle. I love a good triangle. Right, and now you can tell me, well, you're always going to get Faraday's constant because it's in the data book, but you can tell me the number of electrons that's involved if you're given this, or you can give me the, by just doing that cover up thing. I feel I'm making less and less sense as this term goes by. Right, what we can do is we can take our law 1, our law 2, and we can combine it. So this is 2, or 1. Remember, you've got to make sure you're looking at the right one. And we can see there's some commonalities about the two. There's commonalities, and it means we can push them together. Every example I've seen has not done that putting them together. They've worked out one and worked out the other. And you're going to have to go by the marks and how confident you are with it. So there's no, I don't think I've really seen any examples where they've just skipped to the end and they have put these two together. But if that's the way you are inclined, you can see that so you can look and see these are combined, but I'm going to suggest probably you don't use this unless you get to that point where you're really confident with it and you think it's going to save you time, but most of them have not really used this, I'm going to say. So we have a can that we want to cover with tin. So our tin cans, we have our beans or whatever in. Oh my God. So I've got a power pack. So a setup this apparatus, it would be much bigger and more impressive in real life. It would not be so one piece. So this is my metal can that I want to cover with my tin. What I do is, this is now negatively charged because I've attached it to the cathode. This is my power supply. This is my anode, which is the tin. So it's a piece of tin, then it's in this tin nitrate. So what happens is you get these little ions coming off, these tin 2 pluses, and we've got them in the solution. And what happens is this is attracted to here, and, you know, they can start breaking off here as well, and it just forms a thin layer over here. And what we can do is we can do some calculations with this. So we can do some calculations with this to work out, well, how much metal am I going to get on my thing? What's the expected? So you'll be thinking about what the ideal amount is. Who knows if that's actually what you're going to get? You know, you've got standard lab conditions, that's going to affect it. There might be surface area, there might be impurities, there's all these other things that mean you won't necessarily get actually what you want. If you ever do, you'd probably be a bit suspicious. So I've got this set up and we're going to measure how much tin. Is that what my question was? Yeah, I want to know if I leave this, how much tin am I going to get on my can? So, I've got to say so wrong. That's very annoying. So I set this up. I leave for, how much time did I say? 13 minutes. Put my current of 3 amps in, and I want to know so the example would have more than that, but really any question you should be able to break down and you should be able to say, like, do these steps. So taking out all the waffle and all the other stuff, what are they asking? What are they giving you? What are they asking you? So what are they giving you? What are they asking you? How are you going to do it? So I've got my time here. can use my three different equations to work out what I've got here. So it's that kind of tricky. You've got to remember the steps, you've got to think about it logically, you've got to have kind of an estimate about vaguely where you are. So if you start getting to a weird number, you don't go off on one, like off on an adventure. So you still, get some marks, but the idea of, are they going to ask me with 2 tons of tin meal on this question? Like, is that a reasonable thing to do? So first I work out my charge. Someone's playing some tunes. Right, so I've got my 3 amps. So that's my I. And then I've got 13 minutes times 60 to get my seconds. So remember, this needs to be in seconds. So I need to convert this into seconds. I'm hoping I don't have to tell you how to do that. That would be pretty scary. So I've already worked this out because I have to, otherwise I can't do it in my head. So that's my charge in column. Now I need to find my number of electrons. So my number of electrons that are involved in this lovely reaction, so I know what my mass is. So the number of electrons is equal to, oh, I've deleted my thing, very useful. Oh, they divided, write it down. Is Q over F. Remember the triangles? I can't work these things out, but it makes it much easier for my brain if I have those triangles to remember how to do it. So I've got those triangles, Q over F. So I've got this number here, 2340 over F Faraday's. So that's in the data book, and that is 9650. So that gives me, if I can write, 02 425. That's how many, my number of electrons. So I have this many electrons being involved in my reaction. But I've got a 2-to-1 ratio of my electrons and my metal. So I'm going to need twice as many electrons as the metal. That doesn't make sense. So for each mole of tin that I get, I'm going to need 2 moles of electrons, because it needs to make that balanced. So how do I work that out? I just take this number and I go 0.02 425 by 2, and that gives me how many moles of tin are going to be consumed in this reaction. So then that gives me that's how many moles of tin. Now I want to know my mass, so I have to go back to my year 11 chemistry, year 12, the stuff we just assumed we remember, and to work out our mass we use our mole mass. So look this up on the periodic table, and that is 0.012 times. So that's the molar mass, and then that gives me and my numbers were 1, 2. Anything else that's smallest? Oh, 1. Oh, that's annoying. So I've got 1 gram, which just really hurts my heart. So I've got 1 gram of tin being deposited on my can in my 13 minutes if I run it at 3 amps. So that's what we will need to do. We also need to work out the time. So I'm not going to, I've already talked twice as much as I should have. I'm not going to give you the time, I'm going to give you an example and give you some practice at doing. So Faraday's second law is mostly used with the first law and combined to work out how much of something we need, how much time, how much energy, how much, and time, energy, and mass. Time, current, and mass. Whereas in the study done, make sure you understand that there's a reason why we care about those things. It's not just there's a mass. Ooh, great, hurrah. It needs to be a reason. Right. Bye.